In this podcast, we're going to talk about percent yield. There are three different kinds of yield. There are theoretical yield, actual yield, and percent yield. Percent yield is when you have the actual yield divided by the theoretical yield and then you multiply by 100. The actual yield is going to be what you actually get in lab through experimentation. And then the theoretical yield is going to be that what you would calculate if everything went according to plan. So it's what you calculate basically, because when we calculate, we assume that everything will be perfect, everything will go according to plan, and we won't lose anything. So percent yield, again, is actual over theoretical, which is what you got, what you actually got in lab, over what you should have gotten, your theoretical, times 100. All right, here's an example. We see that aluminum burns in bromine, producing aluminum bromide. So first thing we need to do is we need to write an equation. So we have aluminum, and that's going to burn in bromine. That means it reacts with bromine. And there's something special about bromine. I don't know if you remember. It is a diatomic element, so we got to have that 2 down there. And that produces tells us we're going to use the yield sign, aluminum bromide. All right, so we got Al and Br. Al's 3 plus, Br's 1 minus, so when you swap and drop, it'd be AlBr3. All right, now it says that we had 6 grams of aluminum, and that reacted with excess bromine, so we have extra bromine, and then 50.3 grams of aluminum bromide were actually produced. All right, so this will be your actual yield right here. This is what we got when we did it in lab. So there's our actual yield. Okay, once the other two types of yield, which are going to be our theoretical and then our percent. So to do our theoretical yield, we're going to do a simple stoichiometry problem. First, let's make sure our equation's balanced. Get these bromines balanced. All right, and then balance the aluminum. Okay, now we're balanced. All right, so we're going to take our 6 grams of aluminum. We're going to use stoichiometry to find out how many aluminum bromides we should have gotten. All right, so molar mass of aluminum is going to go on bottom, 26.98. All right, and that's 1 mole of aluminum. All right, now we're going to use mole ratios from the balanced equation. We have 2 moles of aluminum, and we're trying to get to aluminum bromide, and we see that we have 2 moles of that as well. Okay, and then lastly, we are going to need to get to grams of aluminum bromide. So we're going to need to know the molar mass of aluminum bromide. I figured it out for us ahead of time, and I got 266.685. All right, now we're going to multiply everything on top, divide by everything that's on bottom, and we get 59.3. Okay, and this is our theoretical yield. Okay, so that's our second yield that we were asked to find. Now we got to do percent yield. Percent yield is going to be actual, which was 50.3, divided by theoretical, which we just found in our equation. And then we're going to multiply that by 100, and that's going to give us our percentage. And we see that we have 84.8%. Okay, So percent yield, theoretical yield, actual yield. Okay, let's look at a different problem. All right, here we are given the equation and it's already balanced. Tells us that the percent yield has been proven to be 74.3%. Says we have 10 grams of Hg and 9 grams of Br2. How much Hg, Br2 will be produced. So basically this is a limiting reactant problem here. So let's go ahead and find out which one is going to be the actual limiting reactant so we can figure out the total that we're going to produce. So we got right, there's our mercury. Molar mass of mercury on bottom is 200.59. One mole. All right, and then you see we have 1-to-1 ratios, so I'm going to skip the writing and just put 1-to-1 here because everything up here is a 1-to-1 ratio. And then we want to figure out how many grams we're going to have. Okay, and let's see, the molar mass of HgBr2, because that'd be our product. Alright, and I got 360.39 for the molar mass of HBr2. Alright, and when I multiply across and divide by what's on bottom, I get 17.97 grams. Alright, so that's the first step. Alright, now we got to do that all over again, but this time we're going to use 9 grams of Br2. Okay, molar mass of Br2 on bottom, which is 159.8. Alright, and just like in the previous problem, because all we're dealing with is 1-to-1 ratios, I'm just going to put 1-to-1. And then the last step, we're going to convert to HgBr2. Which had the molar mass of 360.39 grams. Okay, and that gave us 20.3. Okay, so that told us that this is really the theoretical yield right there, and the Hg is our Lr. Okay, so this is the first part. This is our theoretical, but we know that actually we don't get 100% yield. So we got to go back and figure out how much actually will be produced. So we need to figure out the actual yield. All right, so we got 74.3% is the known yield. We're looking for the actual. And we know the theoretical is 17.97 grams. And of course, can't forget times 100 part. All right, so we're going to divide by 100 first off. And that gives us 0.743 is equal to actual, I'm going to abbreviate it as A, over 17.97. And then you're going to cross multiply these two. And that tells you that the actual yield is 13.4 grams. Okay, so that's how much you actually make right there of the HgBr2. Okay, the second part of the question wants to know if it did go to completion, so we're going to assume that it did have 100% yield, which it really didn't. and 17.97 grams were used, or made, excuse me, of the HgBr2, how much of the excess, the bromine, would be left over? Okay, so we're going to need to take the yield that we would have gotten if we'd went to completion, okay, and we're going to convert this back to Br2. Okay, we know the molar mass of the HgBr2 is 360.39. Alright, and that's 1 mole HgBr2. Again, we only have 1-to-1 ratios. We can just shortcut a little there, 1-to-1. Alright, and then we want bromine. So we're going to have 1 mole Br2, and then the molar mass, which is 159.8. Okay, and see how much bromine we would actually use. Okay, we'll multiply all that out, and I got 7, so 7, even though it kind of looks like a 2, 7, 7, 7, okay, 7.968 were used. Okay, and then we know that we started with 9 from the original problem. So 9 minus 7, and starting to do my tails again. Alright, and we get 1.032 left over. Unreacted. Okay? Alright, and one last problem. Tells us that we have brass, which is a mixture of copper and zinc. Says that we reacted according to this equation. The zinc reacts with the hydrochloric acid to make zinc chloride and hydrogen gas. The copper does not react. So it wants to know, if we had this much brass and we produced this much zinc chloride, what's the composition of the brass? Okay, so we're going to have to work backwards on this problem. So we know that we started with 0.0985 grams of ZnCl2. Okay, and we need to convert that to see how much Zn we have. Okay, we know that the molar mass of ZnCl2 is 136.296 grams. Okay, now we're going to use mole-mole ratios. We have a 1-to-1 here, so I'm going to shortcut again. Alright, and then we need to get it to grams of zinc. Okay, and we know that our molar mass of zinc is 65.39 grams. Alright, which tells us that the amount of zinc that we would have had originally was 0.0473. Alright, now we can divide that by the total of the brass mixture, which was 0.5065. That's brass. And that tells us that, oh, and we're going to multiply it by 100 because we're going to do mass percent here. And that will tell us that we have 9.3% zinc by mass in that brass.